So, having discussed about the conductor material selection, we will move to the design criteria. What should be the design criteria? Two important aspects of any current conducting path: thermal and the electrical. And electrical side, I say resistance or resistivity. On the thermal side, it is a conductivity or overall ability to remove dissipate the heat. So, the important aspect of that is, whatever your heat generation by the conductor should be always less than what is the capacity of heat removal by natural convection mostly. So, for any conductor, electrical conductor, what Ohm's law says, the potential drop is nothing but I into R. Now, you move, but this resistance of the conductor material, this resistance, when I say conductor resistance, is dependent upon the material property and the physical dimensions. How it is related? The resistance R is equal to electrical resistivity rho multiplied with the conductor length and divided by the cross sectional area. When I say cross sectional area, so the area through which current flows. So, if current is flowing like this becomes cross sectional area, and the length becomes the length through which the current flows. Problem is that this resistivity is a function of temperature. If it is a constant, it is quite easy to bring all the solution from this equation itself, but this resistivity is a function of temperature. And how it is related? Resistivity at any temperature T is a function of at reference temperature multiplied with the coefficient and delta T from that reference temperature. So, 1 plus alpha delta T or T minus T 0. Now, current carrying capacity of a bus bar is limited only because of its temperature constants, nothing else. If you are able to remove the heat and maintain the temperature, you can literally take infinite amount of the current from that, but then the temperature should not change. That means, whatever the heat is getting generated, you should be able to remove it. If not, then the temperature keeps on rising. As temperature keeps on rising, the conductor resistivity keeps on rising. So, temperature keeps on rising, resistivity keeps on rising, ultimately your heat generation keeps on rising. If heat generation keeps on rising, your temperature will keep on rising. At certain temperature, it will melt and you cannot carry any further current. So, the current carrying capacity of a bus bar or conductor is limited only by the maximum acceptable temperature. And who sets this maximum acceptable temperature? As a designer, we set that my temperature should not go beyond plus 10 degree of ambient or plus 15 degree of ambient or plus 5 degree of the ambient. Means that when I say ambient, that means when the system is in equilibrium. So, the simple relationship, the heat generated by Joule heating, that's happened because of the current flow into the conductor. That should be less than equal to the heat dissipated to the ambient by the conductor. If it is less than, the temperature will not rise, it would be maintained. If it is equal to, also the temperature will not rise, but if it is greater, if this heat generator is greater than the heat dissipated to the ambient, then temperature will keep on rising. So, what happens initially the heat generation would not be sufficient for, would be more than the heat dissipation. So, your temperature keeps on rising, but at a certain level a equilibrium takes place. Now, since your temperature start rising, your heat dissipation also start rising. So, at some particular level your heat generation and the heat generation and heat dissipation both becomes equal, and that is what the design limits we put. Generally this delta T should not be more than 10 degree in the regular application. Based upon the material or the thermal management system, it could be anything else also, but on the regular way generally we consider around 10 degree delta T plus 10 degree. So, now you have equation I square R, that is nothing but the Joule heating. S is the shape factor. Shape factor means how your bus bar or conductor size is. It is a regular shape or it could be a curvy shape. Depending upon that, this S value keeps on changing. Should be less than the heat dissipation by convection. Now, this has to be solved iteratively, because your resistivity is your resistance is the function of resistivity, and the resistivity is the function of temperature. So, temperature keeps on changing, resistivity keeps on changing. So, it has to be solved iteratively. As the initial case, one can consider 2 ampere per mm square as a current density. Solve it iteratively, you will find. Now, this delta T you have already fixed, I you already know, R you already know, because R keeps on changing. H is generally known. What you do not know is area. You will find out the area. Now, you know also the cross sectional area, the length cross sectional area. With this all the things together, you would be able to find out what should be the your conductor material or conductor length or conductor cross section. Let us go for example here. A bus bar, while conducting maximum current, attains a maximum temperature of 47 degree centigrade. Now, what you require, the length of conductor is fixed, because I know where my first cell, where my second cell, and if this both the cells has to be connected, what should be the length? The length is fixed, and that is nothing but 60 mm. Now, I have also fixed the cross section area of the conductor. Generally that should come from the design criteria, but let us suppose we have fixed the conductor cross section, and that is nothing but 2 mm into 10 mm. So, this is the cross section and this is the length. Now, consider the material is copper and the room temperature is 20 degree centigrade. We need to find out the resistance of the bus bar. All the data has been given, alpha copper and resistivity at 20 degree centigrade. Now, if we are going to solve, so what we have to find out? The resistivity at 47 degree centigrade, and that is nothing but resistivity at 20 degree centigrade into 1 plus alpha we know, T minus T ambient, T 47, T ambient 20 degree. So, that is nothing but 1.902 into 10 to the power minus 8 ohm meter. Now, we also know the length. So, the resistance is nothing but R resistivity into the length divided by the cross sectional area, and which turns out to be 5.70 into the 10 to the power minus 5 ohm. So, 60 mm is how much? If you would have seen, my cell width itself was around 20 mm when I was talking about the cell prismatic cells, where I talked about 8P 8S configuration, and later we came down to 2P 16S configuration. So, one cell width itself is 20 mm. Now, if I have to connect 8 cells together, so my length of the bus bar will go to 160 mm minimum. Now, if I take the same cross section, so it is a 2.5 times of this one. That means in some milliohms the resistance will come. Now, let us suppose it is a 1 milliohm. Let us suppose your conductor resistance is 1 milliohm. Now, you are drawing the current of 100 ampere. What would be the heat generation? 100 into 100 into 1 by 1000. So, it would be almost 10 watt. 10 watt is huge amount. You can still work out using natural convection or a forced convection, but the 10 watt is a huge amount of the heat getting generated. If you convert it in hourly, in the energy form, it is a 10 watt hour. That could give a vehicle can take from such type of pack around 40 watt hour to 50 watt hour energy consumption in running per kilometer, 3-wheeler, a good 3-wheeler, and then 10 watt hour is your almost waste. This is 20%. So, what you will do in that case? I will also increase the cross sectional area of the conductor. So, as soon as I increase the cross sectional area of conductor in such a way that my overall resistance comes down, then I will go in not even a milliwatt, maybe microwatt, and then my energy consumption will, because of the heating of the bus bar. Heating is nothing but it is a waste. You cannot utilize that energy anywhere, or I will reduce the current. In both way, if I am able to do, I will be able to reduce my wastage of the energy. In short circuit scenarios, what happens in the short circuit scenarios? When short circuit happens, generally the current would be very high, flow of current would be very high. Because of the high flow of current, there would be high rate of the heat generation. If there is a high rate of heat generation, there would be high rate of temperature rise. If there would be high rate of temperature rise, what happens? First, your insulation will melt, because generally that is made of some types of plastics or rubbers, which melting temperatures are quite low. Then the local melting will start happening, which you can see here in this picture, here, especially here. So, local melting started happening. Now, once local melting started happening, after some time that part will fail completely. That is one part. Second thing, what will happen? This melted material will fall down some nearby. Now, it is flowing, that melted material is flowing. That will damage the nearby part. Already, because of the convection or conduction, the local part has got heated up. Now, a molten material is going over that one. This will further damage the system. So, how do you compute the rate of temperature rise during the short circuit? Again, there is very small formulas for that. The delta T rise is nothing but resistivity divided by Cp into the density of that material multiplied with current density, a square of the current density. I by A is nothing but current density. So, generally you would know what would be the short circuit current, 300 ampere, 400 ampere, 500 ampere. Based upon your bus bar design, you would be able to know this and the current density. So, now you have this delta T rise, you know that what can happen. So, you can design efficiently nearby your conductor path or bus bar path. So, even at that temperature, your design is still safe. Now, if you see, for a copper, the temperature can rise from 20 degree centigrade to 300 centigrade during short circuit scenarios. The resistivity, if such things happen, becomes almost 1.6 times. because of the temperature rise. So, that means more heating, more heat generation, faster temperature rise. So, what is important to know? What could be the delta T rise? How much more temperature it can go? If you know the current density, what you have designed for, and since you can get all those values either iteratively or by approximation, then you need to design the nearby parts in such a way that it can sustain. It should not allow any accidental issues there. It mitigates if there is any other structural damage which can take place by a proper design during the design phase. In case of no protection, this bus bar will melt and heat up the nearby components. What are the mechanical considerations we have to work out? Since mostly the bus bars are routed openly, you do not route in some casing or something, you have insulation materials over that one, but generally it is routed openly. So, when it is routed openly, you do not have too many points where you can fix it, you have very minimal point. So, the mechanical reliability, when I say mechanical reliability, it is a structural damage, bending, shear, compression should not happen. So, you have to select a material which not only select a material, the thickness, width, all in such a way that it should not have any issues even with your what do you say, mounting points or fixing points. It should be able to handle stresses because of the temperature, because of high temperature, or we say thermal stresses or thermal deformation, because it is going to heat up. The only thing what you can control during the design phase, it should not heat up more than this. But then once you know that this is going to be heat up to this much level, you need to also design it should not deform during that time. Now, you keep on increasing the thickness, its weight keeps on increasing. Now, it starts deflecting because of the self weight. So, you also have to worry it should not deflect or bend because of its self weight. It should be able to withstand the vibration which it will encounter during the running conditions, during the transportation. How do you calculate the design parameters? A single bus bar attached at two terminals, you can consider it as a fixed beam with both the things, and then do all the calculation, mechanical calculation, find out the deflection, find out the natural frequencies, find out the modes, find out what type of vibration it can sustain, do all the simulation, do all the experiment. Now, this is about component level. Then later on extend those analysis and experiments at the pack level. Now, once you have done all the things, test it and evaluate all the functional satisfaction and requirement. Two conductors are in parallel or anti-parallel and DC current is running, which is generally in case of battery packs. So, there is a electromagnetic force acting upon. You also have to worry, not too much, but still you have to worry. Now, this conductor or bus bar need to be insulated, mostly because of safety aspect, EMC, EMI, and then again thermal, because of these three reasons. So, insulation selection is mostly driven by operating voltage. For lower voltage, you do not have to worry much, but if the voltage is going to be very high, then the breakdown strength, you need to worry about insulation material which breakdown strength or dielectric strength is sufficient enough for that voltage. Operating temperature, both higher side at lower side. Some materials at negative temperatures become brittle, some materials at higher temperatures become ductile. So, you have to also specify the temperature range during your design consideration, or you have to take care that this is the temperature range it is going to operate, and these things you feed it into BMS. If anything exceeds beyond this, let us cut off or reduce the functionality. If IP rating is not done properly, this insulation, especially insulation, can absorb some moisture. The conductor like copper can form oxide layers. If you are using other steel type of conductors, it can form rust. So, all those things has to be taken care during this one. This could also increase your contact resistance, moisture absorption. It could increase the creepage from where up to which length the moisture can be absorbed. Common insulation materials are Nomex, Tilder, Mylar, Kapton, epoxy glass, heat shrink tubing, epoxy powder coating. These are generally a common conductor materials used for insulation of the bus bar. Now, what happens if you keep on increasing the thickness? If you keep on increasing the thickness of the insulation material, it starts decreasing the dielectric strength, because generally the air is considered as the very high dielectric strength. Any material are generally inferior to the air. So, you keep on increasing the insulation thickness, your dielectric strength comes down. So, there is always trade off up to what thickness you should go. However, it decreases the bus bar capacitance. You increase the thickness, it decreases the bus bar capacitance. But higher the capacitance, you have less EMC, AMI noises. So, whatever you say, you consider dielectric strength or the capacitance, it is advisable to have the thin insulation material, but very thin. The thermal aspect, you would have seen the insulation material requirement. So, if you go higher thickness, that is again a problem. If you go lower thickness, is also a problem. You should have a optimized thickness. So, all those three things one need to worry about in conductor insulation selection. Now, one question here, one example here, bus bar sizing for 2-piece cell, what the pack what we have shown earlier on that. A 60 volt 28 Ah battery pack is being used in two-wheeler electric vehicle at environmental temperature of 30 degrees centigrade. During experimentation, it was found that the copper bus bar heats up to 40 degree centigrade when 14 Ah current flows through it and releases a heat of 0.01 watt. Determine the thickness of bus bar if the length is fixed at 60 mm and width is constrained at 20 mm. So, you have length 60 mm, width 20 mm. So, you need to find out the thickness. So, assuming a constant current discharge of 0.5 C, that is nothing but 14 Ah. Also find the voltage drop in each bus bar at 40 degree centigrade. Sorry, in bus bar, resistivity at 40 degree centigrade is given directly. So, simple, heat generated should be less than the ambient heat dissipation. So, the Q joule for equilibrium condition, the Q joule is nothing but is equal to Q convection, and that is I square R, and that has been given 0.0 watt. So, the R is equal to current is given. So, you find out what is the resistance, that is nothing but 5.10 into 10 to the power minus 5 ohm. Now, since you know the R, so R is nothing but resistivity into the length divided by cross sectional area. You know resistivity here, length you know, cross sectional area you know width, you do not know thickness. So, you find out the thickness. So, what is the thickness? 1.15 into 10 to the power minus 3 meter. So, this is the exact. So, you may not find a material of this thickness. So, you have to go to the nearby standard material. Also, this is just sufficient for heat generation equal to ambient heat dissipation. What you want? Ambient heat dissipation to be slightly more. So, you go to the nearby material on higher thickness and that comes 1.2 mm. The next is the voltage drop across the bus bar, and that is nothing but V equal to I R across the bus bar. When I say there is 14, I is 14 and then resistivity you have already. So, one bus bar, that is what we have talked about here. We know the resistance here. So, that is 0.000714 volt. So, final bus bar dimension, what we can say, 60 mm into 20 mm into 1.2 mm. So, 60 mm is the thick length, 20 mm is width and the 1.2 mm is the thickness. So, this is, so now here it is easy because all the temperature has been given, but let us suppose you do not have the temperature, then you fix a temperature, the design temperature, and then move on iterative solution, and then you find out the thickness which satisfy all other conditions. Okay. So, let us move ahead with the design criteria. Whatever we have talked about, we have solved one example problem, bus bar sizing for a 2P cell. There we have tried to find out what could be a thickness of the bus bar, what could be the voltage drop. Obviously, in this question was a simple question, in the sense we have given you all the data, the temperature and the resistivity are the same temperature. However, when you are going for the designing, during that time you may not be knowing the exact temperature, you may be you may have to find out what could be the ambient temperature, can go maximum, sometime it is 45 degree, sometime it is 50 degree. Then you put a design criteria over that one, that is okay, plus 10 degrees my delta T, and then based upon that you solve iteratively and come back with the what could be the thickness, and that thickness may not serve as a standard material thickness. Then you go to nearby higher side thickness. So, when you go for the nearby higher side thickness, that is both the things, you get a standard material from that, and the second thing is that your heat generation becomes less than the heat dissipation with that thickness.